just updated the schedule on the website again yesterday, and let's take a quick look at that. Look at the plan for the next few weeks. So today we are done for the slides, and next Monday will be in 602, and I'll also do an introduction, but I will probably project my monitor to a computer monitor or to a big TV. Do a quick introduction to the joysticks, and then you'll start working on that one for a week. And homework 5 will be that joystick tutorial. And then Rfid, it's a shorter tutorial. That one is pretty short, it's easy. I think you can probably get it done in 2 classes. And then there's another one which will take you more time. It's the homework 6. There are 2 parts. Part 1 is on a PDF. So totally 6 problems, and one of them is very practical. This is actually from in the laboratory of Dr. Michael Grubb in the chemistry department. And during the past summer, he asked me if I can generate a pulse which just follows a pulse generated by a laser. And the laser's pulse is being received by a photodiode, and eventually it's being converted into the voltage. So it's just a voltage pulse, right? And the voltage pulse has a certain width on that, which is, depends what you want to use. So I suggested that you can use 400 microseconds for this one as well. Okay, for the first one. So the first one, the black one, is the input, and that's the output your Arduino should generate. And the time delay should be 800 microseconds. And there won't be just a one pulse. If you use a function generator to create that series of pulses, so there will be several or quite a few of them. It's going to happen. So the pulses are going to happen. It's like a square wave, but the duty cycle is only 20% or 10%. So there will be a series of pulses, and your Arduino should detect that pulse and create another pulse, just follow that pulse with an 800 microsecond delay. And after that, you still have to reset it. So pulse means you have a high voltage, have a low voltage, right? Just pulse. So every time Arduino receives that input, it should generate that pulse after it with 800 microsecond delay. It's a very simple problem, but I think this involves a lot of programming techniques I want you guys to know. I mean, the reason I want to bring this up is since I feel this is very fundamental, but one of the students worked with me during the summer who were in my controllers last year have been trained on that technique, programming technique, but eventually he forgot how to do it. Still need my help. So I think it's better to repeat it or apply that what you have learned into a new practical problem in real world, right? So that's one of them. The first one is pretty simple, just to demonstrate the calculation or demonstrate which one is more sensitive. I have done it in a class. And this one, so I'm gonna introduce that sensor in the slides pretty soon. It's an ultrasonic sensor. And MPU6050, that's the one we have been using for many times. And if you haven't used that before, I have many tutorials. I will refer 2 of the tutorials to you. And you just follow the tutorial and try to repeat the examples, and you'll get there very soon. It's not difficult at all, right? So learn how to read the registers in the sensor and how to communicate with the I2C protocol. Joystick, and eventually the encoder, okay? 6 very, very practical problems. So that's part 1 of homework 6. And part 2 is a short RFID. And I'll introduce the Rfid in the slides pretty soon as well, so you can understand what are these. So we do not need another lecture to cover Rfid joysticks and ultrasonic sensor, all this kind of stuff. Because everything has been covered in the slides I'm going to show you very soon. Right. And homework 6 has 2 parts and a lot of work. So that's why it's due by the end of this month. We'll have a lot of time to work on that. And you can see these days we do not have any lectures. So I give you the time to work in the lab. I'll be there because if you are not familiar with function generators and the equipment, I will be able to help. Okay. All right, that's a plan for the recent, I think, 2 to 3 weeks. So let's wrap up the sensors and actuator stuff. I mean, we have covered that last time. Okay, so for this one, if you have heard about, if the measuring or the displacement range is within a few millimeters, you want to consider this laser displacement detector. $200 on eBay, used ones, works really well. I think resolution is in the nanometer range. So that's something you want to know. I've done that last time. So the PMTs, transimpedance amplifiers, CCDs, CMOS imagers. So for the CMOS imagers, it's a very popular topic since about 20 years ago, 20, 30 years ago. After CMOS technology has been become very popular. You have been in my logic at least, right? Logic or analog or other classes. You understand what our CMOS is? They are just low power and can be fabricated on a very small scale. And right now, it's the smallest one is what? For the commercial product, 5 nanometers from TSMC. And the next one will be 2 nanometers. It's only tens of items for each transistor. It's crazy. So that's CMOS materials. And that's why we can integrate millions of and sometimes billions of pixels in a little tiny area. And that's a camera chip. Okay, that's a camera. So the camera chip is actually a CMOS chip. And you just lay out a photodiode. It's just a pin junction for each pixel and a little capacitor to hold the charge, and then a row decoder, and then a row of ADCs. And that's it. So usually the CMOS imager chip is slightly bigger than the other dies we have because you have to have a relatively larger area to receive enough photons or to host all these millions or billions of pixels. And every pixel has a photodiode, has a little capacitor. You can imagine that. You have millions of or billions of them on one single chip. So if you open up the lens of a high-end camera, you can twist it and you just look inside, you can see a chip inside. Have you ever seen that before? So the surface of that chip is kind of reflecting the light, something becomes purple and it's just colorful. So that's the CMOS chip. So the cover is usually a filter, and what right underneath the filter is the passivation layer of the CMOS chip, just silicon dioxide. And underneath that will be the top metal of the CMOS chip, just all the metal traces. So there are still many people are trying to work on the CMOS technology to improve the speed, the resolution, the aspect ratio. So the aspect ratio is a ratio of the area of that photodiode divided by the area of the pixel. So because only the photodiode is photosensitive, but the capacitors are not. So that's why it's kind of the trade-off. You want to integrate more functions into that pixel, but the thing is you don't want to use a lot of areas for something is not photosensitive. Then you are reducing the aspect ratio. So all these kind of trade-offs, if you go to graduate school, there might be a PI or a professor is works on the CMOS imager stuff, usually for military contracts. And I can tell it's a good topic. If you get into that one, learn how to lay out these pixels and ADCs for the CMOS imagers. It's super simple, super easy to get a job. There are many companies that are hiring, even for companies like Apple and many military contractors. So these are the transistors and caps in 1 pixel. These are just diagrams, not necessarily exactly what's in the schematic. So the triangle thing is a photodiode, okay, and with a reset circuit, with a row and column decoder. That's each pixel. Sound, and so I have a lot of these ultrasonic sensors in my lab. And so one of the homework assignments in the part 1 of homework 6 is to let you use that sensor and calculate the distance between the sensor and the object in front of it. So I've used that sensor, and because you didn't program the sequencer yourself, because there's a library available, the SR04.h, the header file has that little driver. So you can directly use SR04.distance and directly get the data. Really don't need to program anything. But if you understand what's going on for that sensor, it's actually not difficult to program yourself. Just look at the timing, right? So what this does is it has a transmitter and receiver. So the transmitter will send that ultrasonic the sound to the front, and then it's going to be reflected by the object in the front, and then being received at the receiver. So because the speed of the sound is not really fast, like 343 meters per second, and that's why you can, but a computer can run way faster than that. And whenever the Arduino sends that sound signal, it can set up a timer. And then whenever it receives the reflection, it is able to reset the timer and calculate the duration between the transmission and receiving that signal, at the moment receiving that signal. So after the duration is being calculated, they can just use the speed of the sound to calculate for that distance. And the way to do that is you can look at the pins. It has a VCC, 5 volts, trigger, echo, and ground. Equal, echo. Equal, right? Echo. Echo. Sorry. Forgot. Echo. If you use Arduino pins to send a 5 volts pulse, and the duration, for example, 10 microseconds, it's pretty easy to do, right? Just do a digital write. Just do a digital write to that trigger pin. And then what's going to happen is the sonic burst from the module will be sent from the transmitter. So you couldn't see that. You cannot use a oscilloscope to detect that pulses, right? Because they are just sound. And then the signal will be reflected and being received by this one. So the echo pulse output to user tuning circuit. So whatever. So there will be a pulse will be received by this one and being converted into a voltage pulse to this echo pin. We can use Arduino to detect that, and then the duration will be calculated or be achieved. Let's take a look at that code. You have to write the sequence by yourself, right? So for the trigger pin, you have to start from the voltage low, and then delay for 2 microseconds, and then give a voltage high, and the pulse, just keep the pulse high for 10 microseconds, and then pull it low. So it's just generating a triggering signal. And then there's a function called the pulse in function. Whenever it receives the high from the echo pin, it's going to be able to calculate the duration, directly assign that value to the duration variable. And that duration will be in microseconds. And if you do the calculation, so duration is in microseconds. Oh no, it's in seconds. Wait, it is in seconds. So seconds times 10 to the negative 6. That's the duration for 2 trips, right? So the round trip of the sound. So divided by 2, you got the duration for each trip, a single trip, and times the speed. The speed here is 343 meters per second is the speed of the sound. Times 100, you convert into centimeters per second. So you can calculate for the distance. And that's how you can get 0.0343 as a constant here, because it's being calculated from this part. It's very simple, and so try it on your end, see if you can get the correct values or distance. So I'm going to compare with the library version and see if you can get the same distance. So we're now going to do this piezoelectric material, but you want to know probably, you want to know this sensor. It's another type of pressure sensor. So the pressure will generate the voltage. So this is the type of material you give a pressure, and it's going to directly get charges accumulated on the 2 plates. Very interesting. So you still have to amplify it. So it's called Piezoelectric Transducer. And if you give apply a pressure to the sensor, you can collect the voltage from the 2 plates, and vice versa. If you give a voltage, and it's going to deform that surface or the structure or the shape. So it can be used as an actuator as well. Sometimes depends on the voltage you applied to the 2 electrodes of the, like these 2 terminals of the sensor. It's going to deflect in a different range. So you can use that to actuate as an actuator as well. But we are not going to work on any of these ones. Capacitive sensors. So this is another one I've used during graduate school. It's AD7745. And so I used this sensor to sense the volume of the droplets in between 2 electrodes. And it is a very high resolution AD inside. It's 24-bit. And it's just extremely sensitive. And it's another type of circuit you can see in many IEEE journals. It's another popular circuit called CDC. No, capacitive to digital converter. Yeah, CDC. So it's capacitive to digital converter, because capacitance is a variable input to the sensor, and you can directly get a digital output out of it, which is amazing. So directly it's going to be a serial output from the sensor, and this is from AD. If you look at the name of the sensor is AD something. So this is from AD analog device, which the company acquired linear technology, LT Spice, right? So by looking at the pins, could you tell me what's the serial output? I2C. So it's from capacitance to I2C directly. And so when I worked with this sensor, the sensitivity is around like 4 femtofarads. Do you know what does that mean? So farads is a huge unit. So if you grab a capacitor, for example, 10 nanofarads, is that a big capacitor or a small capacitor? 10 nanofarads. It's like a huge capacitor. 1 farad. It's probably used for the transmission lines. I mean, like, huge. 1 farad. So farads are huge units. Whereas the farad is a huge unit. And so usually if you plug in 2 wires on the breadboard, you have used a lot. And since the breadboard has all these metal pins, has all the plastic materials on the board, and if you measure these 2 pins on the breadboard, so usually you are getting picofarads level. So that it's called parasitic capacitance in between all the holes on the breadboards is usually tens of picofarads. And this one, if you look at the sensitivity of this one, is 4 femtofarads, which means you really, if you use the capacitance meter or the measurement tools in the lab downstairs, you actually cannot resolve the changes of the capacitance change of the input of this sensor. It's when I worked with this sensor, I cannot really, I sit in front of the desk and I got all my circuits built on the circuits. I just cannot brace. If I brace, it's going to change the capacitance reading, and I have to leave it there and just sit on the chair without doing anything until the reading is done. If I brace, it's going to change like tens of femtofarads to the measurement. And not mentioning like if you walk through the bench, it's going to change like 100 femtofarads or something. So it's very, very sensitive. So just let you know this is something exists on the market. For the touch screens, not the details of the technique, but a common sense, I'll let you guys know. So the old school technology for the GPS I bought in 2012, the first time I came to the US for graduate school. So you guys were still in middle school? Not you, but 2012, where were you? Huh? No, 9 years ago, like high school or middle school, whatever. So I bought this GPS, and after a while, I was not able to make the changes. So I was trying to press the button on the touch screen, but eventually it's not responding anymore because I eventually figured out that, and also I found I can use my finger tip to press it, but I have to press it hard. And second, I can use my nail to press it as well. But for a phone, probably nail doesn't work. And I can use a pen to make the selections on the touchscreen as well for the 2012 version. But now I believe this all has been changed because the technology of the touchscreen has been changed. So in the past, I think the resistive touchscreen was very popular, The reason you can use a pen, you can use your nail, you can use a hard tip to touch it is because it senses that touch and make the connection in between. So here, the crows here, they were not connected at the very beginning. So it's like a one wire on the top, another at the bottom. So if you press it, give a mechanical force, it's going to make the connection. And that's a resistive touch screen. So whenever you touch it, it makes the connection, and so can change the resistance of the terminals. All right, that's why if you like what you have been using or doing with your smartphone, you just use your fingertip and slide. It won't happen for this resistive touch screen. So whenever you get a touch screen and you have to press hard to make the change, you can tell that's a resistive touch screen, not a capacitive touch screen. So for the new ones are capacitive touch screens. It senses the moisture because whenever you touch it, the moisture and all the your tissue or the blood vessel, the moisture on your finger will change the regional capacitance of the touch screen, and which will tell the computer the location of the touch. Okay. So that's MEMS technology. For example, the accelerometers, gyroscope can be fabricated in an integrated circuit chip. They have used the MPU 6050 in microcontrollers, and you know how that works. Have you thought about that? Have you heard about MEMS? Micro electrical mechanical systems. So these are actually amazing. So Dr. Jeff Jensen is an expert on that. So he used to work with Sandia Lab. So it's a really fascinating area to do in graduate school. So these people usually just stay in the clean for like weeks to develop a chip. So they are not integrated circuit chips. So what they have on the wafer is they apply a photoresist, that material, you can etch it into a certain feature. The thing is, when you're thinking about a silicon wire or a glass wire or anything in real life, it should be very fragile, right? Think anything easily breaking. But whenever all of these materials, the traces, are being fabricated in a micro and nanoscale, they are pretty rigid. They won't be broken easily, and they can vibrate, and they can swing around on the surface of the chip in a micro and nanometer level, and you won't break them when they are small enough. That's very interesting. So if you can fabricate all these wires on the surface of the wafer, then whenever it's being shaped or being vibrated, these ones will move around and change the capacitance of this because it's nano traces. They can measure that capacitance and convert it into acceleration. So these are all inside that little integrated circuits that are going to use for whole things. Just place every single table and vibrate it, or knock the table surface. Whenever the vibration is higher than a certain level, then give a signal or activate the buzzer, something like that. Okay. The MEMS technology, that's why you can fabricate or integrate the gyroscope or accelerometer in a little tiny chip. So every smartphone has a little accelerometer or gyroscope inside. That's why it is able to sense angle change and also vibration as well. Change the screen when rotated. Yes, that's a gyroscope inside. So RFID, it's everywhere in real world. you have your little Sky card. It has RFID inside. So how that works? It has an integrated circuit chip inside, and also it has a coil. So that coil will receive the radiation from the reader, and the reader not only send a signal to it, but also accept signal from it, and also power it up. Is that amazing? So definitely, you should know that there's no battery in your car. Right? There's no battery in the car. Common sense. Not no battery. So how that works? How it is able to send a signal back? I mean, there's a little integrated circuit, a silicon chip inside. Sometimes being fabricated with silicon, plastic. But let's just think about it. It's a silicon chip. So that's so cheap, right? Low cost. So that chip, the coil is like wireless charger. Whenever there's a radiation, it is able to power it up, and just need to power it up for that half second or quarter second of a second. Okay. And whenever the chip is powered up, it is able to send whatever has been pre-stored in the memory and in the RF form and send it back to the reader. That's how that works. The power and the data.
So the power is induced by like the
Yes. It's like the wireless charger has been used for a phone. So we have an experiment with Rfids. It's a door latch, but we won't fabricate a door, you know, in a shop. I don't think it's necessary. Just try to mimic. There's a door, and but the way that you can tell the door is locked or not is I'm going to use the IR sensor. So whenever the door is locked, you just put your finger on the top of the sensor, so there's a reflection being received. And whenever the door is open, you just remove the finger away from the sensor, and just to represent that the door is open, you know, things like that. It's like a hotel card. So after this experiment, you will find out, oh my goodness, so the hotel access card is so easy. Actually, you can design a bunch of cards and sell it. So it has a MasterCard. So whenever the MasterCard is being scanned first, it has access to the next level, which is writing access to the customer card, which is a bigger one. And you can register as many cards as you like to make it happen. So very quick tutorial and experiment to test it out. And also purchased a lot of wireless chargers. And the benefit of practicing with a wireless charger is, you know, because one of the projects I have been working on, the horseshoes project, you know, they were trying to integrate the wireless charger at the bottom of the horseshoes, but eventually we didn't adopt that idea. Because, you know, it's very difficult to find an area, the safe area in the shoes to host that wireless charger for a long time. So we didn't actually do that. The thing is, by working on this wireless charger module, I bought a lot of modules like this. You can practice on how to regulate the voltage from the wireless charger, the receiver, using a little module, how to regulate it into a stable DC voltage, and then send it to whatever device you are going to work on. I have a lot of wireless charger modules in my office and in the lab. If you want to, you know, try it out, just let me know. But I didn't officially put a tutorial on that in this class. I don't think we have the time to do it. I have to be creative to think about like how to integrate this one to some of the labs, because I think this is very common in real world. Just want you guys to learn all this practical stuff. All right, so that's number 2, and let's go through number 3 really quick. Hopefully we'll finish it. All right, first, the thermostat. So there will be a bunch of temperature sensors I'm going to introduce to you guys here. So the first one is a thermostat. It's a mechanical sensor. Depends on the temperature, it's going to deflect or make a contact to the electrical connection. And this is very common in the fridges. And so my fridge started accumulating the frost in 2019. And I was trying to figure out why is that. So because you probably didn't know that actually not fridge, it's a freezer. On the left hand side, usually the freezer, it has a heater inside. You know that. I mean, think about the freezer. It has a heater inside. It becomes really hot. So here's a heater. And the way to diagnose the problem with the heater is just simply use a multimeter and probe the resistance on the 2 terminals. You know, the heater is very simple. Don't think about this complicated. But it's just a resistor. And you can think about that. If you want to heat up a resistor, you really want that resistor to run a lot of current through it. So if you want to run a lot of current through it, it should have a really small resistance. So this is nothing but a low resistance resistor. So if you probe the 2 terminals, it should be somewhere around like 10 to 100 ohms. That's how you can heat it up. And you know, if your freezer starts building this frost, see if this one is like tens of ohms or not. If not, it's a super high resistance, which means it's probably has been blown up at some point. So it's like mega ohms. It's disconnected in the middle. But if it's like tens of ohms, which means it's fine because it's a low resistance, you can run a lot of current through it and heat it up. And then, so there's no problem with the heater, and usually no problem with the temperature sensor as well. But the thing is, there's a mechanical switch will be turned on and off probably 20 times a day to turn on the heater to defrost all these accumulated ice in the freezer. So this one has been running for 15 years. And I saw a bump on the top, and I directly replaced it, and so the freezer was back to work. So that's a mechanical thermostat. And thermistor have used that many times. It's a very simple algorithm here to do the calculation. This is a conclusion from physics, so no magic here. And another one I want to let you know, because if during the interview people ask you like what type of temperature sensor or humidity sensor I've used, you probably just want to tell them the DHT11, DHT22. You have used that in microcontrollers. And if not, you are going to use it if you take that class. So this is a really versatile one because it is able to sense temperature and humidity at the same time. And there are not too many humidity sensors available on the market, and this is one of them. And the way this guy senses humidity is it has a material, a substrate, will be able to sense that moisture and change the resistance between the 2 terminals of the substrate. So there are 2 connectors. So that material will be able to respond with a different resistance when the humidity changes. So for the temperature sensor, if you look at the what's inside, if you look at here, right? The thermistor, right? A lot of times. That's nice. So cheap. Something like $2 can buy $1 for each or less, $1 or less for each. So it has a thermistor inside and also has a moisture sensitive sheet inside as well, and it converts humidity into resistance. And there's another type of temperature sensor, which is a semiconductor based temperature sensor. So that material changes the resistance when the temperature changes, and then it is able to output the analog voltage. You still have to follow a certain equation from the data sheet, which is here, to convert that voltage output. It's an analog output. Okay, keep in mind. So this temperature sensor looks like a transistor, but it's actually a temperature sensor, but outputs analog voltage for it to convert into a temperature. All right. Is that boring? We're almost there, and it's Friday. Have you any plan? Still have a few slides. Almost. All right. Yeah, let's look at one really fascinating application, which is the one I did for the Pagosa Spring hot tubs. First, the temperature sensor has to be resistant to the corrosive water. It's arguably it's a good hot spring if you want to stay there, but not for a long time actually. Because they didn't even know what's the composition of the water. So it has to be resistant to the corrosive environment. So the metal wrap for the sensor won't work. So whatever inside is actually this little thing, the DS18B20. So that's a digital temperature sensor, has been very popular. And the reason it's very popular is it's converting temperature directly to I2C. It's called a one-wire temperature sensor. And so everything is being encapsulated into this little package. And you connect this one to a microcontroller, it's directly I2C. I mean, it's amazing. So temperature to I2C, so no other like amplifiers or anything is required. Did you realize it's amazing?
It only has this DA and the clock and ground.
No, it's only the middle one. The middle one is it's a one wire. It's a power, ground, and then one wire. So one wire. It's directly sending. After it's powered up, it's directly just sending a digital sequence. And that's why I chose this one, because it's so convenient. And the problem is it has all the pins here, and you don't want to directly just use this sensor. It's going to short the power and the ground in the water. That's why I have to buy something special. So it's already encapsulated that sensor into this package, but it's a metal material. The reason I want to use metal is the metal is more conductive for heat. But the thing is, I don't need it actually. But you can buy. So at the first time, I was trying to use a thermal conductive glue to wrap it up, so it's not. So it's going to be resistant to the water environment, corrosive environment. But that one won't stay long because the glue will it will degrade in the water as well after a few hours, after a few days. So that was not a good idea. So I have to find out another version. So luckily, there's a company directly fabricated a rubber material as a probe, and which is thermoconductive as well. And another problem is, the temperature data is out, but since your microcontroller cannot be directly, placed underneath the top, because you have to send out the wireless signal to the router. And if you put everything underground, then the wireless signal cannot be sent out from the concrete. So it has to be wire or cable, and then the cable has to run on the above the ground to somewhere, like you can have a little box to keep everything inside. So the problem is the transmission line. Whenever you have a digital signal, you have to consider that. That's a really practical idea. I know this sounds boring, but when I was talking about it, I'm very excited because I know this is important. So, okay, I'll make it happen. Keep in mind, you want to send a digital signal for too long. Why? Especially for a high-speed signal. So I2C is kind of slow compared to SPAC. One wire. The one wire carries too much information in there. It's relatively slow, but still running at kilohertz. So 1 second, boom, boom, already oscillated for 1,000 times. Right? So what's happening is it's oscillating so fast, and you have two cables together, or there are power and ground lines. The signal line is oscillating that fast, and there are so many parasitic capacitors, even though you do not have caps, but the metal traces the metal cable and the rubber material outside the cable, and then metal again. It's actually a cap. That's all these caps along the transmission line. So that's why the digital signal will decay or attenuate when they are being sent in a long distance with all these caps. So the problem is we won't be able to send the digital signal for long distance if you do not use a special cable. Okay. But here, first you want to use this sensor because it's I2C. I2C is relatively slower, so you can send it to a longer distance. Right? And second, there's a commercial product available on the market, which is directly wrapped that sensor into that rubber tip. So it's resistant to the corrosive water environment. But the thing is, the cable length is still not long enough. So I searched online. One of the solutions to solve that problem is to use the Ethernet cable. The reason the Ethernet, you can see the Ethernet cable is everywhere, right? They're relatively long because the special design of the cable can reduce the capacitance in between the cables. That's why you can send the signal through a long distance at a relatively high speed through that type of cable. And I just bought a lot of these cables, and you can make use all the tithers and make the cable by yourself by a special tool probably. And I think the longest distance I have tried is 100 meters. It can be even longer, but they didn't try it. But 100 meters, no problem at all. Very accurate data can be received at the other end of the cable. So I have to connect the plus and minus. There are three wires, plus, minus, and data, I2C. But you have many cables here. You just need to use 3 of them. Just pick up 3 of them. It's not sending internet data, right? It's temperature data. So we just need 3 of them, and then make a connection on the other end. And at this end, plugging this one to a female header on the embedded system you have, and to read it out. BMP 180, another very popular temperature sensor, digital, I2C. I mean, if this is so boring, what about the math or physics classes you have been in too? Same? Do you have the same response in physics or math? Yeah. No? Almost. Let's see. So I'll post the slides to the website. This is just something you should be aware of. The brushed DC motors wear out over the time because every time it's there's a friction in between the commutator and the rotor, the shaft. And there's a brushless DC motor, is a brushless version of it. So the rotor rotates instead of the shaft. So there's no direct contact. So can last for a longer time. The DC servo motor has a DC motor and a feedback system, so it is able to control the rotation angle of it easily without a feedback, your customized feedback loop. So stepper motor, we're going to use it for a few times in the semester. I'm going to introduce this later. And here's a piezoelectric, that's the actuator, like I just mentioned. You apply a voltage, it is able to bend. It depends on the voltage intensity. And also at the same time, if you press it, there will be a voltage appear at the two surfaces, from the top to the bottom. So ultrasound transducers are piezoelectric transducers. So it's just respond to the sound and then convert into the voltage and then circuits, right, to the ADCs like that. Joystick, so we're going to do that next Monday and have a good weekend. Done.